Okay. Let's see. A couple other things. So the practice final exams, two of them have been posted on D2L. I will write some solutions for those and record videos of those solutions. I will also then finish recording some videos for the quizzes, the various quizzes we've had, as well as some of the practice quizzes I've not recorded as well. Yeah, I have quite a few things to right now. But I will have those done by this weekend. Anybody have any questions about the final exam? If you haven't already talked to me about conflicts, if you have a bunch of final exams on that same day and you're entitled to move the final, come talk to me. The help room next week will be there will be somebody there from 1 to 5 o'clock every day until the final exam. If you there'll be something to help them during those hours. If you specifically want to talk to me about how you're doing, send me an email and we'll just set up the time. Okay, so we have here some demos. As I indicated before, we were a little ahead of schedule, so we didn't have the beats demo. Remember, beats are when you have two notes that are two sounds that have almost the same frequency. So let's say F1 is the frequency of one, F2 is the frequency of the other. Then you hear this sort of wah, wah, wah sound at a frequency of the absolute value of the difference, F1 minus F2 with absolute values. So here I'm playing, this note here is A. It's 440 hertz, 440 cycles per second. And if I play 440 together with 439, if I calculate the difference, that's easy to do. 440 minus 439 is 1. So I should hear a wah, wah, wah sort of every second. Okay? Well, I'll do that. Okay, so now I'm going to play 440 with 438. So now you should hear it the beats will be 2 hertz, so you'll hear every twice per second. Alright, so I can do it with 440 and 437, so it'll be 3 times per second. Okay, let's do it with 435, so it'll be 5 times per second. All right. Any questions about that? The next demo here is on interference. This one is a little bit more subtle. Remember, if the path length, the distance from your ear to, let's say, this one is called D1, and the distance from your ear to this one is called D2, when the difference between D1 and D2 is an integer number of wavelengths, then you get the signals adding up. They go up and down at the same time. If it's a half of a wavelength plus an integer, like 1/2 or 3/2 or 5/2, then they're doing this. One's going up, and the other one's going down, so they cancel out. So it's a little subtle, but I'm going to turn on it. The pitch is a little bit annoying, but I'm going to turn on the pitch, and then I'm going to rotate it around and see if you can hear the differences in the intensity of the sound you're hearing. Okay. There are differences. Some points need to get softer and they get louder again. That's a big difference. Constructive is when they add up. Destructive is when they cancel out. Questions about that? Okay. All right. For today's lecture, plan was to do a bunch of problems. And I'll take requests along the way as well. Let's start off with a couple warm-up problems that are not too difficult. Let's do them with clickers. Let's see. So this will be a wave problem. Let's suppose we have V. We have a wave like this. Okay, so we have this wave, and the question is, what is the wavelength? Okay, A is 4 meters. B is 0.2 seconds. C is 0.04 seconds. D is 2 meters. E is 8 meters. Okay, and I'll open up the polling on this. Okay, I'll give you another 30 seconds. Okay, if you have not already made a choice, go ahead and do that now. And let's see what people said.
Alright, E is popular, A is also not too unpopular. Okay, so let's take a look. We had a few different ways of writing down waves. Notice, while we're at this, so which way is this wave going? Is it going in the positive x direction or the negative x direction? Yeah, do you guys remember? If there's a positive sign here, it's actually going in the negative x direction. If there's a negative sign here, it's moving in the positive x direction. Okay. Anyways, the form, we had different ways of writing down the wave. We had a sine k of x, k times x, omega t. Another way to write it is a sine of 2 pi over lambda times x plus 2 pi over capital T times t. You can use either one. The fastest one would be maybe to use this one here. Okay. Then we would compare what we have here, pi x over 4 is equal to 2 pi lambda times x. All right. So obviously the x's, I didn't need to write the x's actually, that was kind of pointless. So in order for this to work, everybody sees lambda needs to be 8. Okay. So lambda is equal to 8 meters. Questions about this? Okay, while we have this here, let's just go on to the next problem, and the next problem is the frequency. What, for the same wave, what is the frequency? Okay, and let me try to put this up here, the choices. A is 0.04 seconds. B is 50 hertz. C is 0.02 seconds. D is 100 hertz. And E is 25 hertz. Okay. And I'll open up the poet. Okay, I'll give you another 20 seconds. Okay, if you have not already made a choice, go ahead and make a choice. And let's see what people have said. Okay, E is popular. All right, we can do it several different ways. This time let's use this form. So I have, the wave was up top here. I have pi t over 0.02. That must be omega t. So we have, I just write it down here, pi t over 0.02 is equal to omega t. Obviously the t I didn't need to write. So omega is pi over 0.02. Dividing by 0.02 is multiplying by 50, so we get 50 pi. All right, but then the frequency is omega. Omega is the angular frequency. That's in radians per second. So we divide by 2 pi to get the frequency. And so we do 50 pi divided by 2 pi. That comes out to 25. And so the units are hertz, so 25 hertz. Can't read that, that's HC. Any questions about this? Okay, so if somebody were to ask you what is the wave speed, well, you've calculated the wavelength and the frequency, right? So for wave speed, you just take the product of the wavelength and the frequency. That'll give you the wave. Okay, any questions about traveling waves like this? Are there any requests? Is there somebody that has a problem they would like seen? Okay, then I'll go on to what I was planning to cover. Let's do this one together. Maybe I'll zoom in a little bit. This comes from Waves A. The extra practice sheet I uploaded a few days ago. A couple days ago. Okay, let's do one, let's do 110 first. We are told that a pipe 4 meters long is open at both ends. The speed of sound is 340 meters per second. What are the two lowest frequencies for which the air column supports standing waves in hertz? What are they? Okay. So lowest frequency means, well, if you think about our formula was Fn is NV over 2L. So if I want the two lowest frequencies, I will take n equals 1 and 2. N equals 0 is nothing. There's no n equals 0. So let's just remember what these look like. So for n equals 1, for a pipe that's open on both ends, what I call an open pipe, we have antinodes at the two ends. So we can have this sort of behavior for n equals 1. We can have this kind of behavior for n equals to 2. And the formula is Fn is equal to Nv over 2L. Stick in n equals 1, and we get V over 2L, which is equal, L was 4, and V was 340, and we get 42.5 hertz. And for F2, it will just be twice of that, which is 85 hertz. Okay. Any questions about that? Pretty straightforward. NV over 2L. V is given as 340, N is 1 or 2, and L is given as 4. Okay. Questions? Okay. Now, let's go on to number 111. A piano tuner hears 4 beats per second between his standard 512 hertz tuning fork and a note on a piano. what are the possible frequencies of that piano note? In hertz, into 3 significant digits, the frequencies are what? Okay, we just talked about this with the demo. We get beats between F1, frequency F1 and F2. The beats have, the frequency for the beats are F1 minus F2 with an absolute value sign around it. So I just need to have, because the beat frequency is 4, the difference between the standard tuning fork and the piano string has to be 4 or negative 4. Okay. So if it's 4, then I'll go up by 4, so I get 516. If I go down by 4, I get 508. Does that make sense, everybody? Okay. Good. Any questions? All right. Then let's go on. That was this is coming from the Waves A practice problems. Let's go on to, let's do one from the Waves B practice problems. Let's see, I selected 119. Doesn't look. Yeah, that's good, it's fine. That's fine. Okay, a sinusoidal wave on a stretched string is given, that should be given by, okay, it says y, the displacement is 0.02 times the sine of 20 pi times x minus 400 pi times t, and they want to know the wave speed and the wavelength, similar to the problem we just did with clickers. Okay, so let's do it this way. This time we can write it as a times the sine of kx minus omega t, and we can just read off the thing multiplying x is k, so that's 20 pi. Okay, and the thing multiplying t is omega, so that's 400 pi. And then we can use the formulas using that come with these. So the wave speed is omega over k. So omega is 400 pi divided by 20 pi is 20. And the units are meters per second. If we want to know the wavelength is 2 pi divided by the wave number k. Okay, so remember, these are not spring constants, these are wave numbers. There's no spring in this problem. So 2 pi over k, and that's 20 pi, that's 2 pi over 20 pi. That equals 0.1 meters. Okay. Any questions about this? It's good. All right. Now let's then go on. Are there any requests for problems? Okay, then let's go on. This is coming from practice problems 3H. We do number 12 for a nice Doppler problem. So as a train approaches a crossing at 40 meters per second, it blows its whistle, which when the train is stationary produces a sound at a frequency of 1,200 hertz. So the natural frequency of the whistle is 1,200 hertz. If no wind is blowing and the speed of sound in air is 340 meters per second, the frequency heard by an observer standing at the crossing is what? Okay. All right. So the observer is over here, just standing still. So this velocity of the observer will be 0. The train is approaching the observer, okay, because the observer is at the crossing and the train is approaching the crossing. And so because the train, remember the convention, it's positive if it moves towards the other one. So the source is moving towards the observer. This will be V source being positive 40 meters per second. And so now the formula for the frequency, f prime, that is heard by the observer, is the natural frequency of the source, f, times the wave speed, which is the speed of sound, 340, plus v O, which we said was 0, the observer is not moving, divided by v, the wave speed, minus the s, the velocity of the source, which we said is plus 40. So we plug that in, we get the natural frequency is 1,200 hertz. The wave speed is 340, we said plus 0, and then 340, and then minus 40. We put that into the calculator, and we get 1,360 hertz. Okay, so it's higher than the natural frequency. Any questions about this? Anybody got that? So this is sort of a brief overview of the material beyond quiz 6, which I call quiz 7, but this is stuff beyond quiz 6. Okay, now let's jump back to doing some other problems from previous quizzes, from older stuff. Let's see, there's so many things we could choose. I chose 2 test practice problems from 2B number 8. Okay. So an 8-kilogram object is pressed up against the vertical wall by a horizontal force F. Find the coefficient of static friction if the minimum force F required to keep the block from sliding is 410 newtons. Okay. So they want the minimum, so they're saying that the minimum force needed for this to not move is 410. And what that means is that the static friction force is going to have the same strength as the maximum possible static friction force. Okay. If it was not the maximum possible static friction force, then we could release a little bit of the force and it would still stay there because the static friction force would still be able to deal with it. Okay, so now what we're going to do is we're going to look at forces in the x direction and the y direction. In the x direction first, we have the force F that's pressing the block against the wall, and we have the normal force of the wall pressing back, well, pressing to the right, pushing to the right, and they must cancel each other out. So Fn is equal to F, which is 410 newtons. So you probably could have done that much quicker, just said the normal force has to be 410. That's kind of obvious. Okay, so I said again, because we have minimum force, the static friction force will be equal to its maximum possible value. So Fs equals Fs maximum. But Fs maximum is μs, the coefficient of static friction times the normal force. And so we get 410 for the normal force, and μs is something we don't know. Okay, but why did I copy it twice? Okay, so now what we can do is we can solve for. Okay, now I see the rest of the solution down here. Okay, now what we're going to do is we're going to go in the y direction. Okay, in the y direction we have the static friction force going up, and then we have the force of gravity going down, and they must cancel each other out if the block is not moving. So we have the force of static friction must be the force of gravity, which is 8. The mass is 8 kilograms. So it's 8 times 9.8 for small g, which is 78.4. So we have to have that 78.4 is equal to this static friction force, which is 410 times the coefficient of static friction. And that allows us to solve for this coefficient of static friction. It's 78.4 divided by 410, which comes out to 0.19. Any questions about that? Yeah. So we're talking about, actually, it's in the y direction, right? So static friction is pulling up to prevent the block from sliding down. Yeah. Makes sense. Okay. Yeah. So it's been a while maybe since we've done friction, so remember to brush up on these things. Any other questions? Yeah. Yeah, coefficient is just a ratio of two things with the same unit, so there's no units. Okay, let's go on. Let's see, any requests? Anybody remembering a problem that traumatized you throughout the course that you really want to see done? Okay. Oh, okay. You want to do Atwood? There was one Atwood thing right next to here. Okay, is this Atwood enough for you? Okay, it was right next to it. Sure. Okay, so the two blocks shown below do not move because of friction on block 2. But the pulley is frictionless. M1 weighs 3 newtons, and M2 weighs 10 newtons. Okay. All right. This is not quite Atwood. It's not even moving. So you wanted a real Atwood problem. Right. A real Atwood. Okay, here's the real Atwood problem. 2C. This is from 2C. Okay. The two blocks are connected by massless. Sorry, a little too high. A massless rope and pulley. M1 is 6 kilograms. M2 is 23 kilograms. Friction may be neglected. Let's just do number 3. What is the magnitude of the acceleration of the blocks? Okay. So remember the shortcut way I taught you how to do these Atwood kind of problems. You just draw going upwards the snake-like direction that winds around. Okay, it goes up this way. This is a positive S direction, and then it goes like this, positive S direction. And then we're going to look at both blocks together as one unit. Okay, so if we do both blocks together, looking at forces in the S direction, we have gravity acting on this block here, so we have the force of gravity. Let's just calculate how strong it is. The mass is 23 kilograms times 9.8. That comes out to 225 newtons. Okay. So the net force on, by the way, the weight of this block does not have any components in the S direction. It only has things perpendicular to the S direction. So when we consider both blocks together as one unit, we only have the net force being minus 225 newtons, just the force of gravity pulling down here. Okay, but then we know that the net force in the S direction is the masses, or the sum of the masses, because we're considering both blocks together, M1 plus M2 times the acceleration in the S direction. So when I sum the masses together, I take 6 plus 23, that comes to 29 kilograms. So I have 29 times the acceleration AS. So now I can solve for AS. It's the net force minus 225 divided by 29. It comes out to negative 7.77 meters per second squared. Okay. Any questions about that? It's acceleration. If you wanted to know the tension, once you get the acceleration, you can just simply look at one of these blocks. Maybe the simplest one is to look at this block. The tension has to provide the net force to make this accelerate with 7.77 meters per second squared. The mass is 6, so the force must be mass times acceleration. So 6 times 7.77 comes out to 46.6. Okay. Any questions about this? All right, let's do maybe a couple more problems. Any other requests? Anything you'd like to see? Let's do maybe a conceptual problem like this. Okay, a hand exerting this is coming from your actual quiz, quiz 3. Okay, so this is number 2. We have a hand exerting a force F is pushing 2 blocks across a very smooth surface as shown. The masses of the 2 blocks are M1 and MA and MB. The friction is negligible. What is the magnitude of the force block A exerts on block B? Okay. So how do we do this problem? The simplest thing is to start off with both blocks together as one unit. So we consider both together, A and B together. We have the force going in this direction. Okay, so we can figure out the acceleration of both blocks together. So the acceleration is the net force divided by the mass. In this case, the mass would be both blocks, so MA plus MB. So the acceleration will be F over MA plus MB. But what we want to know is what is the force that A exerts on B. So once we know the acceleration of both blocks, we can just say B needs to accelerate with that acceleration. Okay? So the force that A exerts on B will be the mass of B times the acceleration. We said the acceleration is F over MA plus MB, so that will be MB times F over MA plus MB. Okay. Any questions about this problem? Pretty good. Let's see if there's anything else. Is there anything else on this this quiz that you would like me to cover? This is one of the tougher ones. Yeah, can I take it? Okay, let's go on to quiz number 4. Let's see. This one was a interesting problem. So this is quiz, your actual quiz 4, select number 8. Okay. It takes a minimum distance of 48.96 meters to stop a car moving at 12 meters per second by applying the brakes. Okay. Assume that the same frictional forces apply and find the minimum stopping distance when the car is moving at 26 meters per second. Okay, so the frictional force will be the same. We want to find out how much longer the car will be skidding. Oops, I'm running out of battery on my computer. So let me do that. Okay, so what we're going to do is we're going to use the work energy principle. We have the net work done by all the forces is equal to the change in the kinetic energy. Okay. So let's figure out what is the change in the kinetic energy. So it starts from with 12 meters per second, and it ends up stopping. So the final kinetic energy will be 0. So the change in the work done by the net force will be equal to the change in the kinetic energy, which will be 0 minus 1/2 m times 12 squared. So m here is not meters, but it's actually the mass of the object. So now, what we'll do is we'll just figure out the same thing for the new speed. So if the new initial speed is 26 meters per second, then the net force done by, net work done by all the forces will be minus 1/2 m 26 squared, which is minus 338 meters. So I can compare 338 versus 72. Okay, there's a factor of 4.69. So it needs to do 4.69. No, it's okay. I thought I dropped something. Okay. 4.69 times the amount of work. And since the force is the same, it has to go that much longer in the distance. Okay. Any questions about this? Yeah.
Well,
Oh yeah, you can definitely do it this way as well. Yeah, and that would work in this problem. You would have a braking force that will give you a deceleration. You can find the distance it travels, and yeah, absolutely. Okay. Good point. All these braking problems with a constant force can be done with constant acceleration. All right. Let's see. We have time for maybe one last one. Let's do one last one, then we'll call it quits. Okay. Which one do you want me to do, 9 or 10? 10? Okay. Let's do conservation of momentum. A car moving at a speed of v equals 12 meters per second hits a parked car. After the collision, both cars move together. If each of the cars has mass 1,500 kilograms, how much kinetic energy is lost during the collision? Okay, initially, so we're doing conservation of momentum first. So initially we have just one of the cars moving with 12 meters per second. And then, and the other one's stationary. And then afterwards we have both cars moving together with a velocity v final. But we need the momentum to be conserved, so the initial momentum is m times 12. The final momentum is 2m times v final. And so we can solve for v final. That's going to be 6 meters per second, just half the speed of the initial. Now we can go back and calculate how much kinetic energy we have in the beginning and at the end. In the beginning case, we have the car with mass 1,500. So we have 1 half times 1,500 times the initial speed, 12 squared. That comes out to 1.08 times 10 to the 5th joules. And the final kinetic energy will be 1 half times 2 times the mass, which is 3,000, times the final speed, which is 6.0, square that, and we get 5.4 times 10 to the 4th joules. And so the change in the kinetic energy, K final minus K initial, it ends up being minus 5.5 times 10 to the 4th joules. Okay. Any questions? If not, I'll see you guys tomorrow. Oh, this is saying how much is lost. That's yeah, let me just turn off this second.